All right, today we are diving into a piece of control technology that is seriously shaking things up in some of the most complex industries you can imagine. It's called Active Disturbance Rejection Control, or ADRC for short. And honestly, it's not just an upgrade, it's a completely different way of thinking about how we control chaotic systems. So let's get into it.
So, to really get why we even need something like ADRC, you've got to picture what a modern power plant is actually like. It's this massive, roaring, dynamic beast. You've got these huge time delays, things that change constantly depending on the power demand, and just a ton of unpredictable disturbances. It's not like driving a car, it's more like trying to steer a supertanker through a hurricane, especially now that we need these plants to react in a split second to keep the grid stable.
Now, for the better part of a century, the go-to tool for this job has been the PID controller. It's the trusty old workhorse of the control world, simple and effective. But here's the thing, the game has changed. With renewable energy coming online, our power grid is way less stable. And we're asking these old thermal plants to do things they were never designed for. And these new, modern storms are pushing this 80-year-old technology to its absolute breaking point.
And that is exactly where ADRC comes in. It's so important to get this. ADRC isn't just a better PID, it's a whole new philosophy. It's a totally fresh way of looking at the fundamental problem of control itself.
Okay, the absolute core genius of ADRC comes down to this one idea, the total disturbance. Think about it. Instead of trying to model every little thing, like the friction in a valve, or the changing quality of the coal, or how different parts of the system are interfering with each other, ADRC just says, you know what, let's just lump all of that messy, unknown stuff together and call it one thing, the total disturbance.
And this quote just nails it. It takes a problem that's basically impossible, knowing every single thing about your system all the time, and turns it into something you can actually solve, just estimating the combined effect of all those unknowns. It stops you from chasing ghosts and makes you focus on the only thing that actually matters, which is the total force pushing your system off course right at this very second.
This right here is the night and day difference. A PID controller, it's reactive, it's passive. It has to wait for a gust of wind to knock the boat off course, then it measures how far off you are, and only then does it try to correct. ADRC is proactive. It can feel that gust of wind in real time, and it immediately applies a counterforce to cancel it out as it's happening. It's not reacting to the error, it's actively rejecting the cause of the error. Big difference.
So the big question is, how does it actually do that? How can it feel this total disturbance and just cancel it out? Well, to get that, we need to pop the hood and take a look at what's inside the ADRC toolkit. ADRC is really made up of three key parts that all work together. First, you've got the tracking differentiator, which basically smooths out our commands so we don't jolt the system. Then, and this is the heart of the whole thing, you have the extended state observer, the ESO. Think of it like a detective that's always on the case, figuring out what that total disturbance is. And finally, the state error feedback controller takes the intel from the detective and calculates the perfect move.
Let's zero in on that detective, the ESO, because this is the absolute game changer. The best way to think about it is as a real-time uncertainty sensor. I mean, you can't just go out and buy a sensor that measures modeling errors or weird interference, but the ESO creates a virtual sensor that does exactly that. It gives the controller the one piece of information it's always been missing. It literally makes the unknown known.
So what is this observer actually figuring out? It's constantly spitting out three critical pieces of information. First, the system's current state. What's the pressure right now? Second, its rate of change. How fast is that pressure going up or down? And here's the magic ingredient. It's best guess of the total disturbance. When you have all three, where you are, where you're headed, and what's trying to push you off course, you have everything you need for truly proactive control.
And all that intelligence boils down to this really elegant bit of math. This is the active rejection part we were talking about. So U0 is what you would do in a perfect world with no disturbances. But then ADRC adds this brilliant counterpunch. It subtracts Z3, which is the ESO's estimate of the disturbance, and it just cancels it out. By taking away the disturbance before it even has a chance to mess things up, the messy, complicated, real-world plant suddenly starts acting like a simple, predictable system from a textbook. How cool is that?
Okay, so we've talked theory. Now let's see what this all means in a real head-to-head fight. Let's put the old guard, PID, up against this new challenger, ADRC, right in the middle of that power plant storm we talked about.
I mean, just look at the comparison. The differences are just stark. PID is passive, ADRC is active.
PID gets really fussy if your model of the system isn't perfect. ADRC is basically model-free because it just lumps all those errors into the disturbance it's already designed to cancel. This makes it unbelievably robust to the very things that make PID stumble, like changing conditions and weird dynamics. And hey, as a bonus, it's often way easier to tune.
Let's make this super real for a second. In a big coal-fired power plant, it can take up to 56 seconds from when you feed more coal in to when you actually feel that energy in the boiler. 56 seconds! For a PID controller, that is an eternity. It's like trying to drive a car where there's a 1-minute delay on the steering wheel. It's almost impossible.
So, how does ADRC handle this monster? That 50-second delay? Its effects just get absorbed into the total disturbance, and the controller learns to expect it. The crazy non-linear behavior of the boiler at low power? Yep, that's just part of the disturbance. The sudden demand to ramp up power to keep the grid stable? You guessed it, that's just another dynamic for the ESO to estimate and the controller to reject. It turns all these unique, impossible-sounding challenges into one problem that it knows how to solve.
Look, solving these issues in just one power plant is already a massive win. But when you start thinking about scaling this technology across the entire network, well, you're not just improving one plant anymore. You're literally building the foundation for a much smarter and way more stable power grid.
So let's just do a quick recap of what makes ADRC so powerful. Right at the center, you have its core idea, active disturbance rejection. And from that, you get all these amazing benefits. It's extremely robust against pretty much anything you can throw at it. It has a model-free simplicity that engineers in the real world absolutely love. Tuning is way more intuitive and fast. And, of course, it's proactive, not reactive, solving problems before they even start.
And that really leaves us with this huge, fascinating question. We've seen how it can handle the insane complexity of a power plant, but what else is out there? I mean, think about robots trying to walk on uneven ground, or chemical reactors with weird side reactions, or even rockets flying through turbulence. If you have a way to estimate and reject disturbances, you can bring order to almost any kind of chaos. The possibilities are just massive. Hey, if this explainer on ADRC helped bring a little order to your day, do us a favor and hit that like and subscribe button. We will be back soon with another deep dive into the technology that is shaping our world. Thanks for watching.